Guys, I'm back again with another interesting topic of digital electronics, and you will make sure that you will learn to how to design ring counter and Johnson counter both, and you can also easily design any other counters after doing this class. So let's start and do the needful. Make comments if you do not understand and also subscribe. So let's start. So guys, here we go. This is my ring counter design. Before designing any counter, you have to just know 4 steps. You have to design 4 steps. That is, first one is state transition diagram, then the excitation in table, then K-map, and the final is the circuit design. So in ring counter, my state transition diagram is like that. Here we go. The one which is in MSB, the others are 0 output. This one will be shifted step by step to the LSB, and these 4 are my state transition diagram. Firstly, the MSB will be set 1, others will remain 0, then the one will shift rightwards, then again it will shift rightwards, then again in the LSB, and it becomes to the MSB again. So that's how my output of the ring counter will continue to transition. To make the transition, that is, one will be shifted rightward simultaneously. Now the final is step 2 is excitation table. PS is the present state, NS is the next state, and the excitation inputs. So I have to know what is the present state of the output, then what the next state I want, and to make the next state from previous state, what the inputs are to be given in D flip-flop. So it is a 4-bit ring counter, so there are 4 D flip-flops. Now in the present state, first write down the combination of 0 0 0 0 0 0 0 1 and simultaneously up to 4 ones. You are very well aware known of that. There are 4 bits, so total 16 combinations, 2 to the power 4. And now in the next state, what will happen in the next state? Present state is 0 0 0 0. Now I am going back to the state diagram. There is nothing, all the 0 present. So for 0 0 0 0, the next state will be don't care. All the next state will be D, that is don't care. Now 0 0 0 1, there is 0 0 0 1, so the next state will be my 1 0 0 0. So there it is, 1 0 0 0 0 0 1 0, there is 0 0 1 0, next state is 0 0 0 1, so that is 0 0 0 1. 0 0 1 1, there is nothing, you can find that 0 0 1 1, so all the next state will be don't care. So that's how you have to design this next state. Now excitation input, I know what is my present state, I now know what is my next state, so what the inputs are to be given. The advantage of D flip-flop, using D flip-flop, is that whatever input I will give, the output will be exactly equal to the input. So whatever I have written in the next state, just make it copy paste here. D D D D, there will be D D D D. 1 0 0, it will be 1 0 0 0 0 1, it will be 0 0 1. There is don't care 0 0 1 0 0 0 1 0. So just copy paste, and then after doing that, just move forward to the next step. Now here we go. The next step, step 3, is the K-map. You can see here, I will make you understand only one K-map, because we have to solve 4 K-maps, as it is a 4-bit ring counter. So first there is D3, these are my present state, Q3 Q2 Q1 Q0. Now 0 0 0 0, what is excitation inputs? In D3 it is D, so 0 0 0 0 in D3 it is D. Then 0 0 0 1, it is 1, so again 0 0 0 1, it is 1. After that 0 0 1 0, it is 0. 0 0 1 0, it is 0. Then 0 0 1 1, it is D. Then 0 0 1 1, again it is D. So I have filled up that D10D. Then after that you will need to put all the values in the KMap from that excitation table. So my 16 combinations of D3 are putted here. D1 0D, 0D, DD, then 0D, DD and DD, DD. Now what you will have to do, you will just have to make it a pair. In all, after all the value have been put in the D3, there is, you can see, only one single one is present and all other filled with either D or 0. So in pairing you have to choose the one, and with that you have to choose the don't care and maximum number of don't care to be put. So we may put there is 2, we may have put this 4, and but in this pairing we have used 8 boxes. You have to ignore 0 in that pairing, you have to take 1 and maximum number of combination 1 and D present here, you have to choose that one. So I have choose this 8 boxes which has only 1 and 7 D's. So from here you have to write down the expression of the D3. In overall pairing you can see Q3 and Q2 all are changing. Q1 is also changing from 0 to 1, only one value, that is Q0 is constant, that is 1 and 1. So D3 is equal to Q0. Similarly you have to solve 4 K-maps for D2 which will be equals to Q3, D1 which will be equals to Q2, and for D0 which will be equals to Q1. So now finally I have got the expressions, that is D3 equals to Q0, D2 equals to Q3, D1 equals to Q2 and D0 equals to Q1. So now I have to go for the circuit design. There are 4 bits, so 4 D flip-flops, all the clocks are connected. Now you know D2 is equals to Q3, so Q3 is D2, they are sorted. What is D1 equals to Q2, so Q2 is sorted to D1, D0 equals to Q1, so Q1 sorted to D0, and D3 equals to Q0, so Q0 is sorted to D3, and 4 bits are taken as my output. So that's how you can design a simple 4-bit ring counter. Now if we talk about the Johnson counter, here we can see another name is shift counter. Why that shift counter? You can see 1 0 0 0 is my first condition, first output, that is 4-bit Johnson counter. Then it will be 1 1 0 0, 1 1 0, all ones. Then again from left the 0 will be inserted, so 0 1 1 0 0 1 1 0 0 1, all the zeros. Then again 1 will be inserted from the left side, and that's how the process will continue in the state diagram. This is my Johnson counter. Now again same process. In the step 2 there is excitation table, you have to fill up the present state, that 16 combinations. After all the 16 combinations are done, you have to put the value in the next state. So 0 0 0 there, all 4 zeros, so 4 0, then 1 0 0 0, there is 1 0 0 0 0 0 1, 0 0 1 will be all zeros. Next state from here. Now 0 0 1 0, that is don't care. Why? There is nothing that is 0 0 1 0 present in that state diagram, so again don't care. So similarly you have to fill up the next state diagram, next state table. All the columns are to be filled, all the 16. So as earlier discussed, the next state will be similar to the excitation input in the D flip-flop, so this will be just only copy paste. Then you have to solve the K-maps, 4 K-maps. So first D3, I have put the value according to the excitation table as earlier discussed in the ring counter. So here you can see a pairing of 8 boxes which compromises of 1 and D. So D3 will be equals to Q0 bar, because the Q0 is not changing, that is 0 and 0. As the value is 0, so this is bar. If the value was 1, then it would be Q0. Similarly here D2, Q3 is not changing, that is 1 1. Q2 is changing, that is 1 and 0. And Q1 Q0 all are changing, so Q3 is not changing and having a value 1. So D2 equals to Q3. Similarly D1 equals to Q2 and D0 equals to Q1. Again in the circuit, D2 equals to Q3, here it is. So Q3 and D2 is shorted. D1 equals to Q2, so shorted. D0 Q1 shorted, and D3 equals to Q0 bar. You can see the bar, so it is taken from the bar and shorted with D3, and 4 outputs are taken from here, Q3, Q2, Q1 and Q0. So that's how you can design a Johnson counter. So for any counter design, if I know what is my present state and what is my next state, so if I can design the state transition diagram, I can easily find out the design of that circuit. So that's how you have to design the counter, and that's easy, that's much easy the counter design is. So ECE is very easy. So let's subscribe with Easy ECE and enjoy our video. So thank you. Make comment, share among your friends, subscribe. Thank you.